Amid the gray mist rolling across Chengdu Airport, a tailless metal shape slid quietly along the runway, and in just a few seconds, the world realized China had stepped into the race for the sixth generation. The aircraft that observers have provisionally called J-36 is not merely a flight test prototype. It is a statement of an entirely new doctrine, the fusion of stealth, artificial intelligence, and data connectivity into a system of systems. While the United States continues to press ahead with its next-generation air dominance program, and Europe pursues Tempest, Chengdu appears to have played its boldest card yet. Is the J-36 only an experiment? Or is it a signal that we are entering an era in which aircraft do more than fight they see, think, and make decisions faster than humans? Join Top 10 Discoveries Official as we investigate this right now. Disclaimer: this video is a technical analysis of military technology based on open-source intelligence and expert commentary. It does not instruct on how to build or employ weapons, and it does not promote violence. Any performance figures mentioned, if present, are publicly estimated values and may change when official information is released. In late December of 2024, the first images of a mysterious tailless aircraft painted in light gray appeared at Chengdu Airport, instantly drawing the attention of defense observers around the globe. The prototype, marked with the number 36011, has been informally referred to as the J-36, a next-generation fighter developed by the Chengdu Aircraft Corporation, a subsidiary of the Aviation Industry Corporation of China. A short video lasting only a few dozen seconds revealed a large, blended wing body with no vertical tail, a rare feature even among Western experimental aircraft. Just a few months later, in early 2025, additional photos and videos surfaced across international platforms, showing the J-36 performing flight tests over Western China. Open-source optical data indicated that the aircraft was considerably larger than the J-20, measuring roughly 75 feet in length with a wingspan of about 62 feet and an estimated maximum takeoff weight exceeding 119,000 pounds. However, several differing estimates exist, as no official specifications have been released. Its overall configuration and expansive wing surface have led some open-source commentators to describe it as the largest fighter aircraft ever built by China. Amid the fierce global competition to develop sixth-generation fighters, the J-36 is viewed as China's direct response to America's next-generation air dominance program and Europe's Tempest initiative. Rather than focusing solely on stealth, available observations suggest that the J-36 embodies a new design philosophy, the idea of a system of systems, where each aircraft acts not only as a combat platform, but also as a sensor hub, data link node, and tactical coordinator within a connected network. The development of the J-36 is believed to have begun around the late 2010s, following the induction of the J-20 into service. In the years that followed, Chengdu's research facilities expanded to support aerodynamic testing of tailless configurations, and open-source imagery hinted at a possible three-engine arrangement, a configuration rarely seen in aviation history. Public evidence so far indicates that the J-36 remains in its prototype testing phase, but the public flight test conducted in 2024 marked a significant milestone, suggesting the program had matured enough to advance toward integrated system evaluation. The emergence of the J-36 is more than a mere technical trial. It represents a symbolic moment in China's aerospace evolution. From a nation once reliant on imported engines and composite materials, it is now approaching full independence in developing advanced fighter aircraft, a feat once considered among the greatest challenges for any industrial power in the 21st century. The J-36's design represents a clear shift in thinking. Instead of refining traditional elements, engineers opted for a characteristic combination: a tailless flying wing, a three-engine arrangement, and a diamond double delta geometry to simultaneously optimize two goals that often conflict: high aerodynamic performance and survivability against modern sensors. At first glance, the tailless configuration provides a significant stealth advantage. Removing the vertical tails reduces the upright surfaces that strongly reflect radar waves, thereby helping to lower radar cross-section from multiple aspects. However, this also introduces major challenges in stability and control. To compensate, the J-36 employs a diamond double delta geometry, two sequential delta regions with a kinked leading edge that creates a diamond-like outline which helps balance lift across different flight regimes, especially in the transonic region and during transition to supersonic speeds. Aerodynamically, the Diamond Double Delta yields two clear benefits. It lowers drag in the transonic transition zone and distributes pressure across the wing surface in a way that helps maintain stability without vertical surfaces. The kinked edges and differing sweep angles across the wing regions are tuned to optimize airflow, reduce boundary layer separation, and sustain high-speed performance. Some analyses even speculate maintain control at speeds around Mach 1.8 to 2. At the same time, the wing surfaces are built from composite materials and coated with broadband absorbing layers, aiming for a multi-band stealth strategy rather than focusing on a single frequency band. The three-engine layout is another distinguishing feature. Three engines, two mounted on the sides of the fuselage and a third in the upper rear fuselage behind the cockpit, provide high total thrust, boosting payload capacity and extending operational range. This arrangement also supports potential supercruise at high speed without continuous afterburner use, saving fuel and increasing on-station reconnaissance or combat time. Additionally, distributing intake and exhaust ducts helps reduce infrared signature, a key factor when countering IR sensors. For a tailless aircraft to fly stably, the J-36 integrates a next-generation fly-by-wire flight control system, combining real-time control algorithms with multifunction control surfaces. Thrust vectoring is synchronized with these surfaces, allowing high-agility maneuvers without conventional tails. The flight control software is central. Ultra-low latency, instantaneous response, and large data processing capability are mandatory. Finally, the human-machine factor cannot be overlooked. The cockpit is large enough for two pilots seated side by side, enabling a division of labor between piloting and sensor mission management. Taken together, the tailless plus three-engine plus Diamond Double Delta philosophy turns the J-36 into a platform that fuses stealth, high aerodynamic performance, and system integration designed to operate both as a fighter and as a command node within a modern network battle space. The J-36 appears not simply as an effort to minimize traditional radar reflections, but as a mindset that signals a trend. Stealth must be comprehensive, resisting radar, infrared, and the effects of electro-optical sensors alike. A fitting term for this approach is broadband stealth, meaning the reduction of signatures across many frequency bands and many sensor types, rather than optimizing for a single radar band. Geometrically, adopting a tailless layout in the Diamond Double Delta outline dramatically reduces planar surfaces that face incoming radar, making backscatter collection more difficult. That is combined with surface treatments using composite materials and radar-absorbent material coatings elements that lower radar cross-section at multiple frequencies. But modern stealth does not stop at radar cross-section. Attention also turns to controlling thermal signature. Intake and exhaust placement is designed to disperse hot gases, and active and passive cooling measures are applied to reduce the infrared background, complicating detection by infrared sensors. At the sensor layer, the J-36 does not operate as a single-track system. Large windows for electro-optical and infrared sensors, integrated electro-optical suites, and the ability to connect to data networks enable a passive approach, detecting targets through optical and infrared signals before resorting to active radar, thereby lowering the risk of being discovered. A modern sensor architecture often includes an active electronically scanned array radar in a concealed frequency band, while simultaneously prioritizing electro-optical and infrared and other passive sensors to conduct long-range reconnaissance without exposing position. A key part of broadband stealth is sensor fusion. Data from electro-optical and infrared sensors, electronic signals, radiation warning systems, and data links are synthesized in real time by the onboard processing system. Fast processing enables the aircraft to detect and classify targets without turning on active radar, or to use active radar only in situations that require it. This reduces exposure time and increases survivability on the modern battlefield, where air defense networks look for any sign of emissions. The lifecycle management aspect cannot be ignored. Radar-absorbent coatings, special surface structures, and cooling systems impose high maintenance and logistics demands. A stealth fighter performs well only when rigorously maintained. Shortfalls in maintenance will quickly degrade stealth effectiveness. Therefore, the industrial capability to scale painting processes, replace coatings, and validate signature levels becomes a strategic factor on par with initial design. Finally, all assessments of the J-36's signatures remain inferential. Based on test images and public observations, concrete numbers for radar cross-section or infrared suppression are typically estimates. Even so, it is clear that the J-36 path is not toward a one-dimensional stealth tool, but toward a multifaceted low-signature platform that integrates sensors and data processing to operate passively within complex combat environments. The J-36's weapons bay is more than a magazine. It reshapes how a multi-role fighter conducts missions. The main bay is approximately 25 feet long, with large internal volume that allows the aircraft to carry a sizable weapon suite while retaining stealth when required. Estimated internal payload capacity falls in the range of 33,000 to 44,000 pounds, enough to host long-range missiles, guided glide bombs, or large sensor packages without relying entirely on external wing stations. Concealing weapons within the fuselage is key to maintaining a low radar cross-section during target approach. The ability to carry the PL-17 air-to-air missile, with an estimated range of about 250 miles, enables long-range engagement from safe standoff positions. Meanwhile, glide weapons with ranges of roughly 125 to 185 miles provide precision strike capability against fixed targets. In addition, two side bays along the fuselage can house short-range PL-10 missiles or defensive modules, allowing the aircraft to switch roles rapidly between air superiority, strike, and area defense. This versatility, combined with an intelligent weapons management system, transforms the J-36 from a pure fighter into an airborne cruiser capable of commanding and executing multiple successive missions. The onboard weapons management architecture is modular and highly automated. Algorithms select weapons based on real-time sensor data, shortening target exposure and improving firing accuracy. Bay doors must open and close quickly and quietly without impairing aerodynamics. This demands precision electronic actuators and vibration-resistant materials. A major technical trade-off is balancing bay size, structural strength, and stealth requirements. Bay doors are frequent vulnerability points if not engineered with sophistication. An important development path is integrating directed energy weapons, such as high-energy lasers, into side bays or swappable modules. If successfully fielded, lasers could perform close-in missile defense or degrade enemy sensors without conventional munitions. However, these systems impose heavy demands for power generation, cooling, and thermal integration, requiring the aircraft architecture to supply excess electrical power and efficient heat management systems. The airborne cruiser role is also reflected in coordinated strike capability. The J-36 can act as an airborne command node, passively detecting targets with sensors, relaying coordinates to unmanned aerial vehicles or surface vessels, and then launching long-range weapons from internal bays to destroy targets without closing in. This reduces risk to pilots and escorts while exploiting range and stealth advantages. Yet every technical advantage brings logistical challenges. Maintaining internal bays, ensuring bay door seal integrity, testing actuators, and managing thermal loads for energy weapons are significant maintenance burdens. The practical deployability of these concepts will depend on supply chains, maintenance routines, and certification processes under continuous operational conditions. The J-36's design and sensor suite suggests this aircraft is conceived not merely as a standalone platform, but as a central node in a distributed combat network. The system of systems concept here means each aircraft operates in parallel with satellites, surface warships, unmanned aerial vehicles, and other reconnaissance stations, sharing data, coordinating missions, and allocating firepower in real time. With a two-seat cockpit and a powerful sensor architecture, the J-36 is positioned to serve as a command and control hub within that network. A core element of this model is the loyal wingman idea: unmanned aircraft deployed as wingmen alongside a crewed fighter to carry out high-risk tasks such as signal collection, jamming, or penetrating air defenses. The J-36 can both ingest and process its own sensor data and issue commands and coordinates to these unmanned aerial vehicles. This connectivity requires high bandwidth, low latency data links and a reliable target distribution mechanism that permits weapon employment or remote reconnaissance without the crewed aircraft needing to close on the target directly. The two-pilot arrangement, one pilot focused on flying and the other dedicated to sensors and network management, is optimized for the command role. As the battlespace grows more complex, the tasks of electro-optical and infrared data analysis, electronic warning processing, and tactical decision-making can be split. Human operators concentrate on higher-level tactical choices, while artificial intelligence systems assist with classification, noise filtering, and action recommendations. As a result, the J-36 can assume the role of a sensor network command node in general terms, without specifying exact deployment or operational scope. Software architecture plays a central role. The platform must ingest large data streams from radar, electro-optical and infrared sensors, electronic intelligence suites, and data links, then convert them into a unified target picture for the entire formation. Automated target prioritization mechanisms shorten decision cycles and enable efficient weapons allocation among elements. Crewed fighters launch long-range missiles, unmanned assets perform penetration or decoy missions, and surface ships or shore-based launchers receive precise engagement coordinates. This model also highlights the need to standardize communication protocols, ensure cyber resilience, and operate under contested electromagnetic conditions. An effective combat network requires fault-tolerant links, strong encryption, and the ability to switch to passive modes when emissions become a liability. The management and task allocation system must preserve functionality even when certain nodes are degraded or lose connectivity. In short, if the J-36 is deployed as an airborne command nucleus, its value lies not only in radar or weapons bays, but in connectivity, turning each crewed aircraft and unmanned aerial vehicle into components of a larger system where data drives decisions and survival. This is precisely the approach many modern forces consider central to the future of aerial warfare. Observing the J-36's development sends a clear message. This is not merely an isolated engineering project, but the product of an industrial chain that is progressively coming together. The prototype's public appearance and multiple flight tests in the window from late 2024 to early 2025 indicate that design, aerodynamic simulation, composite manufacturing, and engine testing phases are all active. Many sources say the program is in prototype testing and systems integration evaluation, although no official confirmation has been released. This pattern reflects coordinated capacity across research institutions, universities, and industry, from engine laboratories and wind tunnels to factories producing composite components and production lines for radar-absorbent material coatings. A key element of industrial capability is the engine, the three-engine layout, the requirement for sustained high-speed cruise, and the need to power advanced sensors demand engines with high performance and strong reliability. Historically, a bottleneck for many aerospace industries. If China solves this challenge at industrial scale, it will significantly reduce reliance on foreign supplies and shorten the path to mass production. Equally demanding are the manufacturing processes for stealth coatings, bay door mechanisms, and thermal management systems for energy weapons technologies that require refined production methods and high maintenance capacity. Strategically, faster progress along supply chains and testing has a twofold consequence for the United States. First, it increases schedule pressure on next-generation programs. An adversary approaching sensor-to-weapon integration more quickly forces acceleration of research, testing, and deployment of network systems. Second, the emergence of an airborne cruiser platform with large internal bays and command and control functions could change approaches to fleet protection and regional operations, underscoring the Navy's and the Air Force's need to adjust distributed operations concepts and wide-area air defense planning. However, caution is warranted when extrapolating. The gap from prototype testing to true operational capability is long. Challenges include maturing engines, complex flight control software, material durability, maintenance processes for radar-absorbent coatings, and training for networked operations. Any one of these links can delay or alter the platform's final capabilities. A sensible policy response is to increase targeted investment in critical technologies, high-performance engines, passive sensors, high-bandwidth data links, and secure artificial intelligence systems while strengthening domestic supply chains and allied cooperation. At the same time, ramp up realistic exercises to assess human-manned and unmanned interoperability, and develop maintenance and operational procedures for large stealth platforms. In summary, the J-36's pace of development is an indicator of industrial capability and strategic intent. Its practical significance depends on the transition from prototype to serial production and integration into combat forces, a pathway that will require time, resources, and empirical validation. The J-36 is not designed solely for land operations. Many details indicate intent to extend its operational envelope to the maritime domain, where the interplay of aircraft carriers, launch systems, and networked warfare determines reach and influence. Some analyses speculate on compatibility with an electromagnetic aircraft launch system. But no public confirmation exists that technology enables rapid, smooth launches and can adjust launch force to match a weapon load. Compared with older methods such as the ski jump or steam spring catapults, an electromagnetic aircraft launch system shortens the distance required to reach takeoff speed and optimizes performance when carrying maximum loads. This is particularly useful for a platform with an estimated maximum takeoff weight of about 119,000 pounds and a large internal weapons bay. The ability to take off and land safely on a carrier deck in high sea states requires active arresting and landing systems, a reinforced airframe, and an especially robust arresting hook arrangement. However, this remains hypothetical and no specific details have been published. The J-36 has been reported to incorporate direct lift control solutions and integrated vibration damping features into its landing gear, combined with artificial intelligence-assisted real-time adjustments to compensate for deck motion. When paired with an electromagnetic launch system aboard next-generation carriers, this could enable long-range missions launched from maritime task groups, permitting sorties and sustained operations hundreds of miles from shore. In a maritime role, the J-36 could perform a range of missions: long-range maritime reconnaissance, anti-ship strikes using internal missiles, designating targets for shipboard fires, or coordinating networked operations. The capability to carry long-range missiles and precision-guided glide munitions allows strikes from distances that keep the aircraft in a relatively safe standoff zone, while passive sensors detect targets without resorting to active radar. This employment model can be used to monitor lines of communication, protect sea lanes, or disrupt strategic shipping routes depending on mission configuration. An equally important factor is naval logistics. Sustaining a large stealth platform on a carrier demands a professional maintenance network, from replacing radar-absorbent coatings and inspecting weapons-based seals to sustaining cooling systems for directed energy weapons. Sortie rate and recovery after missions depend on maintenance capacity at sea and in port, as well as supply chains for specialized spare parts. Tactically, when integrated into a task group with loyal wingman unmanned systems and surface ships, the J-36 could act as an air-sea command node, allocating reconnaissance, strike, and defensive tasks. This drives a layered, coordinated approach to operations in which an aircraft not only directly engages, but also orchestrates and amplifies the effectiveness of the whole formation. Nevertheless, the practical effectiveness of this maritime scenario depends on industrializing electromagnetic launch systems, standardizing carrier decks for larger aircraft dimensions, and establishing logistics and training regimes for sustained, complex naval air operations. The path to completing a platform like the J-36 does not end with its first public flight. It is a chain of recurring technical milestones: maturing the engines, confirming sustained high-speed cruise, integrating and certifying the power electronics for high-demand sensor suites, testing the internal weapons bay under realistic loads, and validating the durability of stealth coatings under operational conditions. These elements, not a single impressive photograph, will determine when a prototype can transition to serial production and attain genuine combat capability during the coming decade. Technically, the key indicators to watch are the quality and reliability of the engines, especially if the program targets sustained supercruise, industrial-scale production and maintenance capability for radar-absorbent material coatings, and the performance of thermal management systems if directed energy weapons are integrated. If those links meet industrial requirements at scale, the J-36 could move from prototype status to a widely deployable strategic platform. If not, the program may remain a long-term testbed. From a strategic standpoint, the emergence of the J-36 poses two parallel challenges for the United States. The United States is advancing next-generation programs, such as the Next Generation Air Dominance Program, focusing on networked platforms, advanced sensors, and mixed crewed and uncrewed formations. But if a competitor achieves faster progress in an ability to mass produce, it will increase pressure on timelines, budgets, and international cooperation. The consequence will be that United States programs must both accelerate key research and preserve technological superiority, while also securing supply chains, training, and realistic exercises. Another aspect to consider is the maritime battlespace. As carriers with electromagnetic aircraft launch systems and optimized launch and recovery decks emerge, a platform like the J-36 could exploit carrier reach and networked maritime coordination to conduct anti-logistics operations or protect sea lanes. This demands not only the aircraft itself, but also port infrastructure, carrier deck test mock-ups, and logistics procedures. Compatibility among aircraft, deck designs, and maintenance workflows will be a decisive factor in the next decade. Nevertheless, direct comparisons between the J-36 and United States programs must be made cautiously. The United States retains strengths in core technologies engines, radar, sensors, and software, a wide allied network, and extensive operational experience. In contrast, China may benefit from industrial scale and cost advantages that enable larger production volumes if the program proves reliable. The realistic scenario could become a two-track race. The United States increases investment in critical technologies and allied exercises, while China compresses the prototype-to-production timeline through industrial integration. The final and crucial test is empirical validation. Interoperability within real operational infrastructure, sustaining sortie rates, maintaining RAM coatings, and operating under contested electromagnetic conditions will determine whether the J-36 is a technological symbol or a platform that meaningfully alters strategic balances. Therefore, during the 2030s, indicators should be read on two scales simultaneously: technological progress and practical industrial logistics capability. Only both together will create a true shift on the global aerospace security map. From the first leaked test images to the in-depth analyses of its structure, sensors, and strategy, the J-36 represents a new generation of thinking in military aviation, where technology, industry, and data converge into a single unified ecosystem. While many uncertainties remain about its engines, mass production readiness, and real-world coordination capability, the appearance of the J-36 has sparked a global conversation about the pace of innovation and the very definition of air superiority in the 2030s. The question is no longer, does this technology exist? But rather, how might it reshape the future of aerial combat? In a world where artificial intelligence, multispectral sensors, and virtual co-pilots operate together on a single flying platform, what do you think is the most decisive factor that could make the J-36 a true game-changing aircraft? Its design, its technology, or its system integration? Share your thoughts in the comments below. And don't forget to hit subscribe to stay updated on the latest insights into technology, national strategies, and innovations shaping the future. Top 10 Discoveries Official will return soon with untold stories, projects that push boundaries, and quiet revolutions shaping our world. See you in the next video.